All right, last but certainly not least this afternoon, we have Elle Rock. Elle has joined us from Pomona College, and she's been working this summer, at least in part with Ylva. She won't tell us today, but she's also actually been working on an engineering project with Julia Brady, but she's going to focus her talk today on her work with Ylva. So today she'll be talking about hard ionizing radiation from massive stars, stripped, and binaries, exploring the mystery of the elusive helium-2 radiation. Go ahead, Elle.
Thank you so much, Gwen, for that introduction. We've almost made it. Thank you so much for everyone for their wonderful talks today, and thank you to all the mentors who made it happen. It's been amazing seeing everyone's research, and I'm really excited to share about mine. But first of all, we need to talk a little bit about ionizing radiation. Why is it important to study this at all? Well, it has really wide applicability. If you're interested in, say, the beginning of the universe and early times, maybe you study the reionization of the universe, or maybe you're interested in more recent star formation. In both cases, it's really important to know about ionizing flux. In fact, today, Amelia and Bhavya and Emma all had talks that at least had some important aspect to do with ionizing radiation. But what even is ionizing radiation? Often you'll have something that's energetic enough to radiate photons. And these photons have the right energy levels to kind of knock electrons off of atoms, and it ionizes the atoms. And this radiation is therefore called ionizing radiation. And right now in astrophysics, there's a mystery. There is a wavelength in unresolved galaxies, or in some galaxies, of helium-2 4686 angstroms. And in these galaxies, we have no idea where it's coming from. There are lots of different sources that tend to give off this radiation. We have, say, massive O stars, or X-ray binaries, or shocked ionized nebulae. But there seem to not be enough of these sources to really explain where all of the radiation is coming from. And the reason why this line is so interesting is because this line of 4686 angstroms shows us that there is doubly ionized helium in these regions. And it takes, say, 13.6 electron volts to ionize hydrogen. For comparison, it takes 54.4 electron volts to doubly ionize helium. That's a lot of energy. And so right now, we have no idea where this radiation is coming from. But Ylva, who specializes in binary stars and binary systems, and I are trying to figure out maybe a special type of star in binary called a strip star might hold a piece of the puzzle to kind of solving this mystery. So we need to ask ourselves, what is a strip star? So often you'll have a binary system where two stars are born, but one is born way more massive than the other. And as the old adage goes, as we all know, live fast, die young, big stars do it well. And so this more massive star expands way more quickly than the other star, and expands to the point that it fills something called a Roche lobe. And what that just means is that the outer envelope of this star has gotten so large that it's more gravitationally attracted to the other star than it is to its own core. And so a mass transfer ensues. There is mass from the outer envelope that transfers to the other star, and the other star, called the accretor star, starts taking in this material. We're not sure how conservative this process is, but we know that by the end of it, we have two very changed stars. The originally more massive star is now a super hot, dense helium core with a thin layer of hydrogen on the outside, and the other star has now been energized by a lot more fuel, which was the hydrogen-rich envelope of the other star. And one thing we need to realize before we continue, these are not tiny stars. These stars have a lot of mass. In fact, strip stars, after being stripped, are about the third of the mass that they used to be. And even then, strip stars tend to range from 2 solar masses to about 10 solar masses. So they used to be about maybe 6 to 30 solar masses large, which is nothing to sneeze at. So then we ask, why is it important to even study strip stars? Besides the mystery that I'm interested in? Well, maybe you're like Desiree, who spoke earlier about supernovae, and you're interested in supernovae. Well, type 2b supernovae, which are hydrogen-poor supernovae, it's believed that strip stars are the progenitors. Or maybe you're a LIGO enthusiast like Donovan, and you like studying gravitational waves. We think that the progenitors of lots of binary neutron star mergers are stripped stars where both stars have been stripped by each other. But I personally am interested in the fact that the helium core of the stripped star is so energetic that it gives off a lot of ionizing radiation in something that I'll call from here on out ionized bubbles. And we believe that there is a hydrogen and a helium ionized bubble. Let's go into it more. So the ionizing radiation comes from the star and goes outwards. However, it recombines a certain distance from the star, which has to do with the amount of flux there is. And a lot of stars give off hydrogen ionizing flux and have a hydrogen ionized bubble. However, we believe strip stars are energetic enough that they can doubly ionize helium, and so there will be a helium bubble as well. And let me define the term before we move on. So my title included something called hard ionizing radiation. And hard ionizing radiation is just when the ratio of the helium ionized bubble to the hydrogen ionization is really high compared to other stars. Sweet. So we're interested in the ionized bubbles around strip stars. However, strip stars are really hard to find. Because they're so energetic, their radiation is pushed into the UV. And so we can't really see it because the atmosphere is opaque to UV radiation. But we're hoping, because now we have our first survey, which of course comes from the Swift Space Telescope, that we might be able to actually observe for the first time these ionized bubbles around strip stars. However, we need to know what we're looking for. So I used Ylva's spectral models of strip stars to try to find out and make predictions about the Strömgren spheres, which is just a fancy name for ionized bubbles, how large they are, whether we can resolve them, and whether they're bright enough to actually maybe see, and maybe we can start solving this mystery. So we begin with plots. First, I looked at the ionizing flux of both O stars, which is another type of star that we think gives off a lot of helium-2, actually we know gives a lot of helium-2 radiation, and then strip stars. So on the x-axis, we have the hydrogen ionizing photon emission rate, and on the y-axis, we have the helium ionizing photon emission rate. And the reason why we plotted this is we wanted to see, do strip stars truly have hard ionizing radiation? Well, we have the strip star sequence here, the O stars, and this one-to-one line, however close you are to that line, shows you how hard it is. So the closer you are to the line, the harder the emission is. And surely, the strip star sequence is closer to the one-to-one line than the Mason sequence. So even though sometimes the strip stars have less hydrogen ionizing flux, it has really comparable helium ionizing flux. And that's really promising, because maybe that means that the sizes of these ionized bubbles might be quite large. And that's exactly what we look for next. So now we're looking at the radius of the hydrogen ionized bubble on the x-axis, and the helium ionized bubble, fully ionized, on the y-axis. And again, we have our strip star sequence and our large O stars for comparison. And we see that for these bubbles, for the hydrogen bubbles, we have something on the order of a parsec or a few parsecs. And for the helium bubbles, we have something on the order of about half a parsec. But what's really, really exciting about this is not just the size, because okay, we know the size, but what does that really mean? We need to know if they're resolvable. And as I said before, we have surveys in the Magellanic Clouds, so that's where we're going to be looking first. And it turns out that for the Large Magellanic Cloud, which is about 50 kiloparsecs away, anything that is above about 1/10 of a parsec is actually resolvable using a telescope such as, say, the Magellan telescope that Carnegie uses down in Chile. But we cannot be, oh, one more thing. The smallest strip star that seems to fit that bill is a 3 solar mass strip star. This number is going to show up a lot, so remember it. But we can't be too excited just yet, because in order to know if we can observe these at all, we need to know if it will be bright enough to see. So after characterizing the sizes of the Strömgren spheres, or the ionized bubbles, we need to look at the luminosities. So again, we're looking at the H beta line luminosity, which is just a hydrogen transition. And then the helium-2 line luminosity at the specific line that we've been looking at, the elusive mysterious one. And we plotted the luminosities, but what does this really mean? This isn't actually that useful to us right now. We should look at the ratios between the nebular line luminosity and the star's line luminosity, because we want to see if the ionized bubble is brighter than the star at helium-2 4686. And we actually find that above this particular star, the ratio should be greater than 1, which means that this ionized bubble for helium-2 4686 should be brighter than that line for the star. And again, we find it's the same 3 solar mass strip star that's at the threshold. So that's exciting. So putting it all together is this plot that I had on my poster, where again, we're looking at the hydrogen ionized bubble radius on the x-axis and the fully ionized helium bubble radius on the y-axis. And we see that anything within this box will be resolvable with a typical seeing of our Magellan telescope. And everything that is a star marker is a strip star that is bright, as in brighter than the star itself. Sorry, the nebula is brighter than the star itself in the helium-2 4686 line luminosity. And again, it's a 3 solar mass strip star that is the threshold. So that brings us to our conclusion. Not only do we expect the Strömgren spheres or ionized bubbles to be resolvable, we expect them to be sufficiently bright for stars, strip stars, greater than 3 solar masses. And this is exciting because it means that we could possibly start to look through our data and see if we can actually find this. So that's our next step. We're going to look through our survey that we have and see if we can actually find anything. And hopefully at some point soon, we'll do a specific observation run and see if we can find anything there as well. However, we have to ask one more question. Like any good scientist, we need to know, what if we don't find what we're looking for? For example, the survey is still ongoing in terms of parsing all the data and getting all the spectra and seeing what's going on. But I wanted to show an example of the 4686 line around the normalized spectrum of a 4 solar mass strip star. We have a problem. This is a photospheric, meaning at the surface of the star, absorption feature. What we really want to see is an emission feature that's kind of thin. It goes up like this and back down. So where is the line? Well, we haven't done extensive work on this yet, but during our research, we have taken our models that I've created and we've started looking at different densities, because throughout this entire project, we've been assuming a fiducial density for gas of about 100 particles per centimeter cubed. And this is pretty typical for H2 star-forming regions, so pretty reasonable to assume. However, we found through preliminary looking at our models that it seems that the threshold, right now it's 3 solar masses for it to be resolvable and bright, it changes as the gas density changes. So maybe if we don't see the radiation, then we're looking at a really dilute medium that's really, really sparse and not dense at all. But then that begs the question of where does this radiation go? Well, we're thinking it probably travels out and it might leak into maybe the interstellar medium, maybe the circumgalactic medium, maybe even the intergalactic medium. And these are questions that we would like to address as we continue looking at the survey and figuring out what exactly are we looking at and can we find these helium-2 bubbles. But hopefully we will find Strömgren spheres, because that would be very exciting. Anyway, that's what I have for now. Thank you so much for listening. And I'll leave up this slide. If anyone has any questions, they can be inspired by our musings.
All right, questions for Elle.
Okay, so you kind of just mentioned that what if you don't find anything, and what if it's like very diluted? I was just asking, like, wondering whether you can go like rewind time a little bit to look at what this strip star looked prior to being like diluted and something like that. Like, is there a simulation you can use, or are you working based off of purely observational data?
That's a really, really good question. So we are using sort of spectral models of current strip stars and how we think they behave. But that's a wonderful question, and I will definitely ask Ylva about it, especially since the process of the stars being stripped and binary interaction is so important. So thank you for that.
Thanks for the shout out, as well as the other ones that you gave out as well. I'm just curious, you're gonna continue to work on this project, right?
I am.
Okay.
So our next steps are going to actually be refining our models for different densities and sort of cleaning everything up so we can look at different line luminosities. Because even though solving the helium-2 4686 mystery is really interesting to me and really important, and probably interesting to lots of other astronomers who have been wondering what is causing this radiation, it will also be useful to look at other lines to look for maybe different types of radiation that people might be interested in. So we're going to adjust it for different densities and different lines, and hopefully be able to also solve the questions we posed on this slide. Yeah, thank you.
Great, and one last question.
Yeah, I'm just a bit curious. So when a strip star becomes like stripped, and then the accretor star kind of like absorbs all of the other stuff, can it like, once that process like happens, can it like reverse?
Yes. So at the very beginning of the talk, I talked about how if you're interested in, say, gravitational waves and binary neutron star mergers, the progenitor is actually a system where this star, here I'll use the laser pointer for those on Zoom. So this star has been stripped, has re-energized this star with more fuel. Depending on where it is in its evolution, it'll probably continue expanding as well, and it might fill its own Roche lobe and begin to transfer mass back to this star. I don't know much about that process, but it's very interesting, and I'll look into it more. Thank you.